Welcome to the Launching the Field-Oriented Control (FOC) motor control application using the KD240 Drive Starter Kit demonstration. The demonstration begins with an overview of the AMD Vitis motor control libraries used for field-oriented control, followed by setting up the AMD Kria KD240 Drive Starter Kit with the AMD Kria KD240 motor accessory pack. It then covers booting the starter kit, loading the firmware, and running the motor control application. This demo requires the Kria KD240 Drive Starter Kit, which includes the K24 SOM, a carrier card, and a thermal solution. The demo also requires the following additional hardware included with the kit: a power supply and adapter, a microSD card, Ethernet and micro USB to USB-A cables. In addition, a host machine with a display and the Kria KD240 motor accessory pack are required. The Kria KD240 motor accessory pack includes a 24-volt BLDC motor plus encoder with load disk, a QEI encoder cable, a 24-volt motor power supply, an XT60 power supply adapter cable, a motor connections cable and unused motor sensor interfaces, an assembly plate with 4 mechanical screws. The AMD Kria KD240 Drive Starter Kit acts as an evaluation platform for the K24 SOM focused on motor control and power conversion applications. The KD240 and its base K24 SOM support full user customization through the AMD Vitis Unified IDE, customizable acceleration overlays, and AMD Vivado Design Suite hardware board files. This integrated combination of hardware, platform, and software provides a quick out-of-the-box experience for developers that can then be leveraged for product designs. The KD240 Field-Oriented Control (FOC) motor control application demonstrates general inverter and motor control examples using AMD standard IP and libraries. These IPs, libraries, and drivers showcase the K24 SOM's capabilities to implement applications requiring precise control of motor speed and torque while minimizing energy losses and system noise. The following FOC-based motor control methods, which can be implemented on the KD240, provide an overview of the motor field-oriented control library functionality. Each method focuses on controlling either the torque or speed of the motor. Torque control is the default FOC control, and it maximizes motor torque output consistency by optimizing the quadrature, Q vector, representing useful motor torque, and minimizing the direct, D vector component. In this mode, the goal is to maintain constant motor torque by adjusting motor speed. Speed control is implemented via an additional PI controller that adjusts motor torque to maintain a constant speed. Field weakening control increases motor speed by trading off optimal torque. This is achieved by adjusting the relationship between the Q vector and D vector in the FOC. The block diagram here illustrates the censored FOC application's implementation. Motor voltage and current feedback are provided by the ADC hub. The QEI encoder provides the measured RPM from the BLDC motor as feedback to the FOC control block. The generic PWM block provides a series of on-off commands for each switch of a 3-leg inverter. The gate drive pin control blocks and enable block translate the PWM functionality provided by the SWM PWM HLS IP to the KD40's specific gate drive circuit implementation. The gate drive enable signal, shared across all 3 power bridge phases, enables the power stage. The KD240 motor control block provides motor fault generation and system fault protection logic, which checks for gross system failures such as shorted motor windings or a failed phase leg. All the soft IPs are supported by kernel drivers using the Industrial I/O (IIO) framework. These drivers simplify hardware configuration and usage through features such as buffer support, a common sysfs interface, and integration with the libIO framework in user space. A motor control application library integrated with the device drivers enables seamless operation across different modes. The dashboard GUI allows users to control various set points and gain parameters, as well as observe live plots of key metrics such as speed, feedback current and voltages, and torque. Before you get started with the AMD Kria KD240 Drive Starter Kit and run your first application, and even before you power and boot the board, you will need to download and flash the AMD Kria KD240 Drive Starter Kit image to a microSD card. At that point, you can then run a number of pre-built accelerated applications to start evaluation of the platform capabilities. Let's first look at how to flash the Ubuntu image onto the microSD card. Identify a compatible SDHC microSD card and insert it into your host machine. Download the Kria KD240 Drive Starter Kit image from the URL identified in the Kria SOM Getting Started guide. Flash the downloaded image onto the microSD card using an SD card flashing tool. Once this is successful, remove the microSD card from your host machine and insert it into the KD240 Drive Starter Kit microSD card slot at the J11 port. Now let's take a look at how to make all the necessary connections to the starter kit. First, take an Ethernet cable and plug it into the PS-ETH port labeled J24 on the board. This connection will provide internet access, which we'll need later to download the factory-loaded firmware. Next, take the USB-A to micro-B cable. If you're using your own, make sure it supports data transfer and connect it to the J4 port. Now, take the motor quadrature encoder cable and connect it to the KD240 single-ended SE encoder input port, which is labeled J42. We'll now connect the motor itself. Connect the motor's three-phase connector to the KD240's motor connection port labeled J32. To provide power to the motor, we'll use an XT60 adapter. Connect this adapter to the KD240's DC link port labeled J39. Now connect the motor's 24-volt DC adapter to the XT60 adapter. Do not plug the wall adapter into the AC wall outlet just yet. Ensure you connect the correct 24-volt DC adapter, as it looks identical to the 12-volt DC adapter included with the KD240 Drive Starter Kit. Finally, we'll power on the KD240 Drive Starter Kit itself. Connect the 12-volt 3-amp power supply adapter to the DC barrel jack labeled J12 on the board. Again, do not insert the other end of the power supply into the AC plug yet. We'll power everything on simultaneously a little later. Set up your USB-based UART connection using a serial terminal utility, Teraterm for Windows and GTK-Term for Linux. This demo uses GTK-Term. Launch GTK-Term in the Linux OS and select the appropriate serial port. You should see 4 COM ports enumerated, where the second numbered COM port corresponds to the UART. Configure the port settings as follows. Baud rate equals 115,200. Data bits equals 8. Stop bits equals 1. Flow control equals none. Parity equals none. Power on the starter kit by connecting the power supply to the AC plug. The power LED should illuminate. The AMD Kria KD240 Drive Starter Kit has primary and secondary boot devices that provide isolation of platform-specific boot firmware from the runtime operating system and application. This allows you to focus on developing and updating your application code within the application image without having to rebuild and flash boot firmware. The primary boot device is a QSPI memory located on the SOM, and the secondary boot device is an SD card interface on the carrier card. By default, the KD240 Drive Starter Kit carrier card sets the XCK24 boot mode to QSPI 32. The SOM boots up to U-boot using the QSPI contents, and then U-boot does a handoff to the secondary boot device. After powering on the starter kit, Linux starts to boot, and you can see the log displayed in the serial terminal window. Observe the Linux UART response on the serial terminal program interface to see the log. If you see the heartbeat LED active but no UART response, verify that your machine has the FTDI driver installed and that the terminal program is connected to the correct COM port. At initial login, the Linux image will boot into the following login prompt. Note that the default username is Ubuntu and the password is Ubuntu in all lowercase characters. Once entered, the platform requires you to set a password. Make a note of the password you create for future use. Once Ubuntu has booted successfully, verify internet connectivity via ping or DNS lookup to check your network connectivity. Now that Linux has booted, we need to update the system and add the necessary repositories to access the latest application-specific software. This process may take 10 to 20 minutes. These commands add the required repositories, update the package list, and upgrade the system to the latest versions. With the system updated, install the motor control firmware using the following commands. Install the motor control application. These commands will install the required software components, including the necessary drivers and libraries. To confirm the installation and see the status of available acceleration platforms, we'll use the xmutil list apps command. This command shows a list of available accelerated applications along with their status. The active column here shows which application is currently loaded in the system. On initial boot, a default configuration is loaded in the starter kit, which enables the DisplayPort interface. Prior to loading a new configuration, the xmutil unload app command needs to be run to unload the currently active configuration. Unload the currently active configuration using the following command. Now we're ready to dynamically load the motor control application onto the starter kit. We'll use the xmutil load app command. This prints out the output of the newly loaded drivers based on the device tree overlay that corresponds to the programmable logic bit stream. This application provides an interface to control the motor. The dashboard application allows the user to control the motor and view live plots via a web-based dashboard running on the KD240. We'll start by running the Bokeh server using the following commands. You may be prompted for your password. Once the server starts, take note of the board's IP address as we'll need it shortly. On your host machine, open a web browser and enter the IP address you just noted. This will open the Motor Control Dashboard application. It's important to note that once the server is running, it retains its settings even if you close, reopen, or refresh the browser. When the dashboard first opens, the system is in off mode. Observe that the blue LED DS10 is off. If your unit is connected to a network with DHCP, an IP address will be assigned automatically. If not, you'll need to configure a static IP address. Let's explore the key features of the dashboard. The Mode drop-down allows you to select the motor's control mode: speed, torque, or open loop. Sample size sets the number of data points collected and plotted on the graphs. Samples are collected every 100 microseconds. Due to dashboard performance limitations, the maximum sample size is 3,000. Larger sample sizes may introduce a slight delay in dashboard responsiveness. Refresh interval determines how often the dashboard plots are updated. A minimum refresh interval is enforced based on the current sample size. Larger sample sizes require longer refresh intervals. The gain text boxes allow you to adjust the proportional and integral gains of the control loop. When in speed mode, use speed set point to set the target motor speed in RPMs. The valid range is -10,000 to 10,000 RPMs. In torque mode, use torque set point to set the target torque in amps. The valid range is -2.5 to 2.5 amps. Open loop VD sets the direct voltage for open loop mode. Normally, this should be set to approximately 0 volts. The valid range is -24 to 24 volts. Open loop VQ sets the quadrature voltage for open loop mode. The valid range is -24 to 24 volts. The fault status indicators show any detected faults. A red indicator signifies a critical fault, while a yellow indicator indicates a warning. The Clear Faults button clears any active faults and returns the system to off mode. The electrical data plot displays the currents and voltages for phases A, B, and C. By default, the voltage lines are hidden. You can toggle the visibility of each line by clicking its label in the legend. The current axis is shown on the left if any current lines are visible, and the voltage axis is shown on the right if any voltage lines are visible. The mechanical data plot displays the motor's speed and position. You can toggle the visibility of each line by clicking its label in the legend. The speed axis is shown on the left if speed data is visible, and the position axis is on the right if position data is visible. The live analysis plot displays the data selected for each axis using the buttons on the right. As mentioned, the dashboard initially opens in off mode. You should see that the electrical readings are near 0. Now let's test the different control modes. First, we'll try speed mode. Select speed from the mode drop-down and enter a speed set point, for example, 2,000 RPMs. Observe the motor running at the specified speed. Next, switch to torque mode. Select torque from the mode drop-down and enter a torque set point, for example, 1 amp. Observe the motor's behavior in torque mode. Finally, we'll demonstrate open loop mode. Select open loop from the mode drop-down and use the VD and VQ text boxes to set VD to 0 volts and VQ to 4 volts. Observe the motor running in open loop mode. Now let's see what happens when we apply a larger load to the motor. As you can see, the currents increase and the I-alpha, I-beta circle on the dashboard expands. This shows how you can control the motor application using the motor control dashboard running on the KD240 Drive Starter Kit. The key takeaways from this demo are: the AMD Krea KD240 Drive Starter Kit and its base K24 SOM support full user customization through the AMD Vitis Unified IDE, customizable acceleration overlays, and AMD Vivado Design Suite hardware board files. The KD240 Field-Oriented Control (FOC) motor control application demonstrates general inverter and motor control examples using AMD standard IP and libraries. The motor control application's web-based dashboard running on the KD240 allows users to control the motor in different modes and view live data. To summarize, this demo provided an overview of the Vitis motor control libraries used for field-oriented control. You learned how to set up the AMD Kria KD240 Drive Starter Kit with the motor accessory pack, boot the kit, load the firmware, and run the motor control application in various modes, including speed, torque, and open loop.